Okay, so welcome back to another video. So here we actually would like to calculate what the derivative of x factorial is. So this is actually quite a controversial problem. So what makes this controversial? Well, factorial functions are usually defined for the non-negative integers. So in other words, the natural numbers. So when we think about this in terms of how if we were to map this for the entire real line, so for all real numbers, because that this domain is specifically for the natural numbers, it's not continuous, so therefore that has to give the implication that it's actually not differentiable. So one might say, well, basically the majority is the expected answer to say that no derivative exists for the factorial function. But what if we could actually extend this out a bit, so such that we can map all this towards for everywhere in the real numbers? So that actually where the gamma function comes in handy, because the gamma function is said to be the extension for factorials. So we'll be actually going towards that observation, see what we can do. Now one can actually solve by using the integral representation of the gamma function to particularly find the derivative of what we're trying to achieve for. It's also worth noting that the gamma functions defined everywhere in the reals except for the negative integers when you graph this out. Another thing is that, as I said, that you can solve by using the integral representation for the gamma function. I'm actually personally acts as a follow-up video, we'll be using Weierstrass's definition and then solving the derivative out from there. So if you want to actually check out the whole derivation for specifically both Gauss and Weierstrass's definition of the gamma function, I'll leave that link in the description below for your viewing. But we'll be starting from there, and then just mainly for a disclaimer that you do not have to take my word for this. I'm not saying that this is a definitive answer. You know, it's always good to have like some sort of discussion of whether this is a yes or no for this sort of, questions. So I'm not taking it as this is the correct answer or it's a wrong answer. This is just simply as a way of just extending this out to see what we can further observe and then going into further discussions on whatever you think it's possible from there. So let's actually just jump right ahead. So Weierstrass's definition of gamma says that for gamma of x, this is equal to e to the negative gamma, which is the lowercase gamma is the Euler-Mascheroni constant, and times x divided by x, and then we multiply by the infinite product. So our index starts from k is equal to 1 of e to the power x divided by k. Then we multiply by 1 plus x divided by k and to the negative 1 power, so the inverse. So let's actually take the natural log of both sides. So I have the natural log of gamma of x, then we multiply with, or not multiply, but equal to the natural log of the entire right-hand side expression. And so from here, this is another way to simplify all this out in terms of using logarithmic properties. So we have some addition and subtractions for these natural logs, and then some will cancel each other out. For one, ln of e will just disappear, and we're just left with negative lowercase gamma of x. Then the x is on the denominator, so that means to subtract ln of x. Then we can actually apply some continuity for one that if I have the natural log of the product series, that's another way of saying the summation of the natural logs. If we think about this again, using the properties of natural logs, so this will actually in turn comes down to the infinite sum, starting with k is equal to 1 of, so for one, the ln of e to the x over k, the ln of e gets rid of itself, and so that'll just become x divided by k. Then subtract with, so this is the minus coming outside, so that'll give us minus and then the natural log of 1 plus x divided by k. And so from here, let's actually do a little bit of some differentiation. So we're going to differentiate with respect to x to both sides of our expression. So this is going to give us, so this is the the logarithmic derivative. So this is actually going to be, so gamma prime of x. Then we divide this by gamma of x, again, the logarithmic derivative as it is. Then we differentiate in respect to x to this side, so this is going to give us negative lowercase gamma, subtract 1 divided by x. And then from here, so this is the infinite sum over here, k is equal to 1. And then over here, I'm going to get that this is just 1 divided by k, then subtract. So let's see, I have the natural log of 1 plus x over k, so differentiate that so it's 1 divided by the input, then take the derivative of the inside, so that's just 1 over k, then we multiply the k's from the denominator, and so simplify all that out, so we'll get that this is 1 divided by k, and then add this with x. So this is also nice that because this is gamma prime of x and prime and then gamma of x divided by gamma x, we just took the derivative of the logarithmic derivative of the gamma function. This is actually what's known as the digamma function. So in other words, this is actually following a class of the polygamma function, but this is at the order 0, the digamma. So there's also classes of, throughout the whole polygamma function. So over here, this is just at the order 0, so the first order derivative, you want to put it into that perspective. And so with here, let's apply a little bit of linearity to our infinite sum over here. So let me actually just put a little bit of some writing over here that, of course, I could split this up as the infinite sum from k is equal 1 of 1 divided by k, and then subtract the infinite sum over here, k is equal 1 of 1 divided by k plus x. So it doesn't sound like we've done much, but actually the next step will come in handy from why we actually separated the two from the infinite sum. So with that, let's actually move on to the next step. So this is actually very noteworthy to see over here. So I guess I'm going to put the note over here. So I have that 1 over x. So we're just going to disregard the negatives for now. And then I also have our infinite sum over here of 1 divided by k plus x. So this is actually going to be a very interesting term that we're going to be using. In other words, if we notice that if I were to evaluate this, for example, for k is equal to 0 back into here, that actually gives us exactly up the first term over here. So in other words, this is actually a way of writing this as re-indexing it for k is equal to 0 of 1 divided by k plus x. And then if I actually can re-index back to this again, so put this back for k is equal to 1, then basically that just comes down to just 1 divided by k subtract 1 and then add this with x. And so these two are the same. And it's very nice that I can actually put back that substitution. So now, so far I'll have that gamma prime of x divided by gamma of x. In other words, that's the digamma function. So psi of x for that, the notation convention. So that means so far that'll give us the negative gamma, lowercase gamma, and then we add this with the infinite sum, k is equal to 1 of 1 divided by k, and then we subtract this from 1 divided by k, subtract 1, add this with x. We have some little general formula for what we're doing for x. Now suppose that if I were to put this for the term of x plus 1, so that means I have gamma prime of x plus 1 and then gamma of x plus 1. Nothing too crazy about it, so that'll put us at psi of x plus 1. So we'll just have to replace for x plus 1 in terms of x. So not much needs to be done here, so that means put it back here, k is equal to 1 of 1 divided by k, then that means back here this is just going to be, so put the 1 plus x back, or x plus 1 back into here for x, and so that'll just give us 1 divided by k plus x. And so as we note that, I know I should have wrote this in the very beginning, but I think now it's a good time to say this. So we know that the recurrence relation for x factorial is equal to gamma of x plus 1. So that's one way to put, that's an important key factor to use that here, because if I were to multiply gamma of x plus 1, so for 1, this actually kind of completes everything here. So x plus 1, in other words, that's the same thing as psi of x plus 1, and then multiply with gamma of x plus 1. Okay, and so that actually puts us multiply gamma x plus 1 back to the whole thing, but I could just replace this for x factorial. So let me actually put that under the next line. Oh, and it's also worth noting that gamma prime of x plus 1, as again, going back to that definition, that means if I just take the derivative of both sides, that's exactly what we want to achieve over here. So in other words, this is the derivative of x factorial. Again, you do not have to take my word for this. Then just replace gamma of x plus 1, multiply by this entire thing, replace that with x factorial. And so therefore that achieves that this is equal to x factorial multiplied with negative lowercase gamma, and then multiply with our infinite sum of 1 divided by k minus 1 divided by k plus x. And so just like that, that actually completes the derivation. I guess you could say the supposed derivation for some people who's, I guess I don't want to take any sort, I don't want to put in any sort of insult toward people thinking that this is, the true answer, but, take it as you will. This is the supposed answer that we can actually, that we've actually derived, finding the x factorial. So that comes down to that. So again, let me know what you think about this. So yeah, that's pretty cool if you ask me.